I want to show you another really interesting spatial concept that we use a lot, and that's something called the variogram. Now, a variogram shows us how a data set relates to itself over space. So here's an example of last spring frost dates in the southeast United States. Now, these are about 76 different locations where we look at the last day that there was a spring frost. So you can imagine down in Florida that the spring winter ends and spring starts around February to March. You can imagine in Virginia and areas north of that the winter holds on a little longer. So there you might see April as being a time where there's still some frost on the ground, or a last spring frost. So the last spring frost is actually something that's pretty important in fields like agronomy, because you want to get your crops in at the right time. You want to get them in kind of early, but not too early that they could get affected by frost. It also makes for a rather interesting spatial conundrum too, to find out how does the last spring frost date vary throughout the geography of a particular area. So we often model that in the form of a variogram, and what the variogram is showing is the difference in distance between locations and the difference in their values. So each one of these locations has a last spring frost date. We actually use the Julian date, which starts again obviously on January 1st as number 1 and December 31st as 365. So the question is, if two areas are right near each other, like we see here, you would expect that their difference in last spring frost date should be relatively close to one another. And obviously, as cities get a little further apart, their last spring frost dates will probably be a little bit different. And that's what you see here as part of the variogram. As the distances get larger, the differences between the locations in terms of their attribute also get larger. But then we get to a point right here, which we would call the range, where there doesn't seem to be any relationship. So when we get, in this case, beyond 400 miles apart, these cities don't have much of a relationship, because these are all about 400 miles apart in all different directions. That direction and that direction. So it's basically kind of random what we're seeing here. So that means the data is actually spatially correlated in this area and then becomes uncorrelated. So in the case of last spring frost, and this is in my textbook, cities that seem to be within 400 miles of each other do have a relationship with one another. But when cities become further than 400, there's no longer a relationship. And we can actually model that in SQL. So let's go through and take a look at this formula, and we'll talk it through and show you how we can calculate the values. So in my DB Manager, I've brought in the states and I've brought in the last spring frost values, and you can see them right here. And each one of these last spring frost locations, if we click on one, has information about its average last spring frost date. And again, this is a Julian date that we're looking at. So I can come back in here and let's open up an SQL window. And the next thing I'll do is paste the query in here. So let's bring this down a little bit so we can see it a bit better. So the one thing I want to try and do first is figure out the distance between every station and every other station. So that's the stdistance command, and I'm going to look at LSF as P and LSF as P3. Now the reason we're doing this, of course, is we're comparing the LSF layer or table, last spring frost, to itself, and I'm pretending, as we've done in the past, that they're actually two different tables. So I'm giving them an alias. So this is computing the distance. Now, they are a latitude and longitude based file, so I want to actually calculate the distance over the spheroid. So I'm going to put column true. If I did not have this true, it would return distances in decimal degrees, which is somewhat meaningless. So that's going to return meters. What I'm going to do here is I am multiplying it by this value, which will convert it to miles. And again, if we look back at our our map from before, we're looking at our distances in miles. And notice I'm dividing by 100 and getting the floor. So 125 miles would be 1.25. I would get 1. Miles of, say, 300, again, divided by 100 would be 3. So let's just run this just to show you how this works. Execute that, and that's the values you see down below. So for every point, I'm getting the distance and the difference. The distance in miles, so these are 300 miles, 200 miles, so they're within 1 and 200 miles. This is within 0 and 100 miles. So, and it's telling me how much they differ from one another. So what I really want to get, though, is the average distance and the distance, and I'm going to group it by the distance. Now, I'm also dividing that distance, or that difference, the absolute difference, by 2. Because it's called the semi-variance. That's another part of this this axis here. It's not the actual difference in values, but the semi-variance difference. So it's 1/2 of the distance, the difference. So when we do that, again, it's using our group by statement like we've done before. So I'm averaging that, and I'm getting the distance. Now I've already gotten the distance here. So for all the distance, for all the 0 distances, right, what I want to know is what's the average difference in the attribute value in the last spring frost date. So let's run this one. Okay, so now what we see, the average difference in last spring frost date is 3.9. When it's within 100 miles of one another, 100 to 200 is about 6.82, so about a week, and so on. So we've gone through in this way. And then I'm going to multiply that again by 100, and we'll call that H, because that's the term that we use. And let's execute that. So that's done, and I can select all of those. And as I copy them, I'm going to go into Excel. We'll just paste it here. So here's my H value, my distances between 0 and 100, 100 and 200, and so on. And here's my semi-variance. And as I select these, I can go into the insert, and I'm going to insert a scattergram. And here you can see our values, and I can change the range here. Actually, let me change that. Let's just select the whole table. That's going to be easier. And then we'll select our graph. There we go. So you can see where our 0 to 100 miles is, and we can see what that looks like compared to our variogram here. And I've broken it up a little bit differently in terms of the number of miles you can see. So I used the 100 before. We could have actually changed that to something else as well. But in this example, you can see we have that spot where that range is, where things start. It seems to all work together nicely, and then things go up and down at this point where it becomes a little bit more random. And we can actually do that. If I want to segment my data up instead of by 100 miles, we can do it based on 50 miles, and I'll just run this, and we're going to get some different data here. Let's hit Control A, and we'll copy that, bring it back into here, and we'll paste it. And now that's selected, I can say Insert, and let's insert our diagram. So again, we have a little more variability here that we see compared to the other chart, primarily because we're selecting smaller ranges, but we see again we get to about 400 miles and they're correlated, then it becomes uncorrelated. So again, I show you this because it's just another way that we can use SQL to begin to interrogate spatial databases. And this query that we actually worked with has a spatial part as well as some statistical parts, and putting them all together gives us a very powerful statistical tool to assess how spatially autocorrelated our data is.